Hi, I'm Lisa Joy Zgorski from the National Science Foundation. We don't have spacecraft to take us outside our solar system, yet. Still, astronomers thought they had a pretty good understanding of how our solar system formed, and in turn, how others formed. In the last dozen years, they've discovered nearly 300 exoplanets, planets outside our solar system. Turns out, many of the systems that are home to these planets are not like ours. 3 Northwestern University researchers wanted to know why. Ed Thommes, Soko Matsumura, and Federico Rossio developed sophisticated computer models to explain how these different solar systems may have formed. Their findings are detailed in the August 8, 2008 issue of Science. Through their research, they discovered that our solar system may be the exception rather than the rule. It seems, indeed, uncommon. Dr. Ed Thommes joins us now from Canada at the University of Guelph. Hi, Ed. Thanks for being here.
Thank you very much. It's a pleasure to be here.
Tell me, what are the major discoveries of your research?
Well, what we found is that the process of planet formation is generally actually quite a violent and chaotic one on average, and that the sort of relatively peaceful and sedate outcomes like our own solar system, in which we find ourselves, may in fact be the exception rather than the rule.
How expansive was the research concluding this, and how did you find it?
Well, we ran a lot of computer simulations. We set up simulations which basically tried to track all the important parts of the planet formation process, essentially from the beginning to the end. And so we ran lots and lots of these simulations. We covered a broad range of different initial conditions, different types of starting conditions, and we ran over 100 of these.
Now, one gazes in the sky, sees all these stars, and can't help but wonder, are there planets that surround those stars that are much like our own? What do you think? What does your research point to?
Well, our research, and a lot of the research that's gone before, seems to indicate that the Earth itself, terrestrial planets, rocky planets like ours, by themselves are quite common. They're almost like weeds. They'll sprout up under almost any conditions. But it's the rest of our neighborhood, the big guys on the block, Jupiter and Saturn, that seem to be less common. And while lots of other planetary systems very likely seem to have lots of gas giants like Jupiter, in most other systems we seem to find they look quite different from ours.
Now, why do you think ours is so calm?
Well, what we found in our research is that it's really sort of like Goldilocks and the Three Bears. The conditions have to be just right. And we can have either a case where there are lots of giant planets that form very rapidly, sort of they pop out one after another, and it's this big chaotic mess, and we think that's how we get a lot of these weird-looking planetary systems that we've discovered out there. On the other hand, if the conditions are wrong, then we don't get much of anything. We do still get lots of those little terrestrial planets, like our own, like the Earth and like Venus, but no gas giants, no Jupiters, no Saturns. And in between those two regimes, there seems to be a relatively narrow range where we'll get something like the solar system, when we do get gas giants, but they don't really, the process is not really that violent that forms them.
I've heard Jupiter compared to a junkyard dog, actually protecting the Earth and keeping it stable, enabling life. What do you think of that? Does your research confirm this?
Well, that's a very good point, and that gets at the question of how important to habitability, to life, is the larger planetary environment, not just the terrestrial planet on which we sit ourselves. It's been suggested that Jupiter is basically acting like a bouncer that's intercepting all these nasty comets that want to come in from the outer solar system, from the Oort cloud and from the Kuiper belt, and protects us against comets striking the Earth. So in that sense, Jupiter, something like a Jupiter, a planet that sits beyond our orbit and gravitationally protects us, might in fact be quite important. It's still not fully understood, though, how this effect actually works, because you can also argue that Jupiter put those comets there in the first place. So we still need to understand a little bit better how these different effects actually play off of each other.
So our solar system is uncommon. What implications does that have for actually finding other solar systems like ours?
Well, it may mean that we have to look a little bit harder. In a sense, though, we've been thinking so far that the planets that we found simply looked as weird as they did because those were the easiest to find, these so-called hot Jupiters, planets that orbit very close to their star, closer in some cases than Mercury orbits to the Sun. Those are quite easy to find using the techniques that are used currently. And so one thing that makes planetary systems like ours a little bit more difficult is simply that Jupiter and also Saturn are a little bit further out. And so you have to look a bit harder for the signal that you get using the radial velocity search technique. We've been looking for exoplanets now for going on 12 years, I guess it is. So the interesting thing about that is that the orbital period of Jupiter is about 11 years. And so as we look at these systems over the length of one orbit, we start to get a better and better idea of what's out there. So essentially we're filling out the picture as we look further out. Now, what our research suggests is that we will probably keep finding more and more planets as we look further out, but we may find systems that look perhaps like our own, but maybe with an additional giant planet, an additional Saturn, an additional Jupiter sitting a lot closer in to their star.
Is that what's next with your research?
One of the things that we would really like to look at, I mentioned before the connection between habitability and the larger planetary system environment, and this is something that we would really like to understand better. We would like to understand, is it really necessary to have that junkyard dog? Is it necessary not to have sort of a big rowdy neighbor that's moved in through the terrestrial region all the way to the star? What are the implications of these things? Is it possible, for instance, for a planetary system that consists of no gas giants at all, just little terrestrial planets? We think those are common. Is it possible for something like that to sustain life? So these are all really interesting questions, we think, and we'd like to explore these further.
Are there any limitations to computational power now, and how will supercomputers fit in the future?
Well, in the work that we do, computational limitations really are the thing that we keep bumping up against, and we were only able to do what we did by sort of judiciously simplifying a few parts of the problem and focusing on the physics that was really important. And so the more powerful computers you have, the more computers you have, it's always enormously important. We were quite fortunate at Northwestern to have a cluster of powerful computers, so that was enormously helpful in our research. Having said that, though, of course, any future advancements in computer technology, simply having more computers, more powerful computers available, really allows us to push the envelope even further and to look even further out there and get a better idea of what these different weird sort of planetary systems might look like. Or indeed, if we are the weird system, which seems to be the case.
Ed, congratulations on your paper. Thank you for talking with us about your surprising findings.
Thank you very much. It's been my pleasure.
Again, this is Lisa Joy Zgorski with the National Science Foundation.